This episode of Geek's Guide to the Galaxy is made possible thanks to support from listeners like you. So if you enjoyed the show and want it to continue, please support us on Patreon over at patreon.com/geeks or via PayPal over at geeksguideshow.com/crowdfunding. And to want to give a special thank you to Chris Horn, Timothy Alcock, Andrew Murphy, and Shane Casimir, who all just signed up this week to support us on Patreon, and to Stephen, who just increased his pledge amount. So big thanks again to everyone who's contributed. We really appreciate it. Alright, so now let's get to our show.
Wired.com presents The Geek's Guide to the Galaxy. And here is your host, David Barr Kirtley.
Hello, and welcome to episode 525 of Geek's Guide to the Galaxy. I'm David Barr Kirtley, author of the book Save Me Please and Other Stories, which is available now on Amazon.com. We had a great conversation about the book back in episode 500, so definitely check that out if you missed it. And today's guest is Sabine Hossenfelder, creator of the popular YouTube series Science Without the Gobbledygook. She's a research fellow at the Frankfurt Institute for Advanced Studies, where she leads the Superfluid Dark Matter group, and she's also the author of the book Lost in Math, How Beauty Leads Physics Astray. And in this interview, we'll be discussing her new book Existential Physics, A Scientist's Guide to Life's Biggest Questions. And now here's our interview with Sabine Hossenfelder. All right, so we're here with Sabine Hossenfelder. Welcome to the show.
Hi.
Okay, so I've heard you say that you got into science from reading science fiction, so tell us about that.
Yes, that's right. When I was a teenager, I was very interested in science fiction, and I was fascinated by all the technology that they had and wanted to find out how much of this is fiction and how much of it is science. And so I started reading up on quantum mechanics and astrophysics and rocket science, actually literal rocket science. I was very interested in that for some time. And yeah, so it's maybe not so surprising that I ended up in physics.
So how much of it turned out to be science and how much of it turned out to be probably a lot of fiction, I'm guessing?
Yeah, well, a lot of the stuff you find in science fiction is at least in my interpretation, basically an extrapolation of what we know already. So if you look at all those fancy space drives that they're talking about, like hyperdrives, warp drives, wormholes, all that kind of stuff, they kind of have a footing in the well-established theories, but then they add an extra element of speculation on top of it. For example, you can actually go through those extra dimensions, or you can somehow make warp drives work by some kind of fancy shield or God knows what, or wormholes are actually there somewhere inside black holes, and so on and so forth.
Mm. It's funny because, my dad's a physicist, and he actually got interested in it because he wanted to be a science fiction writer. And so he thought that physics would be a good background for a science fiction writer. And then he just became a physicist and never wrote any science fiction. But he sort of transmitted that love of science fiction to me.
Well, that's interesting.
Yeah. So do you remember, what kind of science fiction did you start out reading? What got you into it?
Oh, yeah. It was, I'm afraid it's a German series, which was quite well known in Germany at the time. It's called Perry Roden. It's very similar to Star Trek. It has kind of some main characters and you follow them for thousands of years, literally. And so it has a lot of the same features, and except that the technology works a little bit differently. And other than that, I was reading everything that was really cheap because I didn't have a lot of money. So they always had these slightly damaged books that they were selling off for 1 Deutschmark. At the time, on this little table in the back. And this is the stuff that I read, a lot of which was like, let's be honest, really, really crappy. It was like really badly written. And at some point, you realize that the big ideas, they always come back, like stuff like the Borg that you have in Star Trek, right? These kind of a group of connected consciousness that sees being human in some sense. Faster than light travel, of course. There's always something with quantum. Quantum is always good for something, and stuff like this.
So was it mostly American science fiction you were reading, or were there a lot of other German science fiction that you were reading?
So the Perry Rhodan series, despite the American name, and if I remember correctly, I think the protagonist is actually supposedly American. It's a German series. But the other stuff, I can't really remember. I read a lot of the classics, like Stanislav Lem and Asimov and stuff like this. And Clark, of course. So it kind of really everything, basically.
Mm. I mean, in your book, you mentioned the story by Isaac Asimov called The Last Question. So is that a favorite?
Yeah,
story
it's one of the things I've always loved. This story. It just, it's very spot onto the stuff that has always fascinated me about physics. This big question, like, does the universe eventually run out into complete darkness, and that's the end of the story, or is there more that we can do with science?
Yeah, I'll say for people who haven't read the story, basically the premise is that there's this supercomputer, and it keeps being asked, is entropy inevitable, basically, and it always says not enough data to answer the question or something, and then eventually the universe does run out, and finally the computer says, has collected enough data to answer the question and says, let there be light, and it turns out that this computer is basically now God and is starting the universe up again. So yeah, I can see how that would appeal, because a lot of your book deals with sort of those sorts of themes. So I can see how that story would appeal to you.
Yeah, it's also, especially this question of entropy is something that I've been interested in for a long time. I don't really trust the definition of entropy that is currently being used in cosmology. So, I mean, entropy is all well and fine if you're talking about thermodynamics and, steam engines and all those topics that it was originally invented for. But when you're talking about the entire universe, I think it doesn't really work all that well. To begin with, we don't really know what's the entropy associated with gravity or with space-time itself. It's like one of those big unsolved problems. But also, entropy is a very, how do I put this, anthropomorphic quantity. If you take it seriously, it tells us about whether it's typically phrased is that entropy tells you something about the decrease of order or the increase of disorder. But this is like really from our perspective, like what we think is disorderly. I think that if you were not to use this human-centric notion of order and disorder, you would get a completely different notion of entropy. And that brings up the question, like, why is any one of them more tenable than any other? To which I don't have an answer, but it's something that I've pushed around in my head for some time.
Right. So I was wondering this. But you do think that the universe will kind of wind down in the end, that human civilization couldn't go on forever because the stars will burn out and, the universe will keep expanding until there's just nothing much going on, or?
Well, that's what the current scientific consensus is, so to say. As I said, I'm very skeptical that this conclusion is correct because I don't trust this notion of entropy. No, I actually don't think that this is what's going to happen, but I don't really have any particular theory to put forward or something. It's just, one of those things where I'm like, yeah, I'm not really sure that this argument actually holds water.
So you think there's some chance that human civilization could continue indefinitely into the future for like hundreds of billions of years or something?
Yeah. I do think so. I think there's just too much that we don't really understand about space and time and entropy in particular, gravity, and so on, to definitely make this statement. I don't think the second law of thermodynamics is as fundamental as a lot of physicists think it is.
Okay, well that's encouraging. Yeah, because I was worried about that.
Yeah. Well,
I was actually...
though I don't think we're going to live to see it.
I was wondering though, when you said basically it's sort of the way we're evolved to sort of see entropy in this particular way. It was making me wonder if you think there might be aliens or AI or something that would have a different perception of entropy and would not share that anthropomorphic view that we have.
Yes, indeed. So I don't know about AI, but one of the common themes in science fiction is that you fairly often have this disembodied cosmic consciousness, which also comes up in the Asimov story at the very end. And if you think about this for a moment, if you have something that's very distributed, let's just say in the entire universe or something, it would have a completely different perception of what is ordered and what is not ordered. So for such a being, entropy could just be something completely different. So I don't know how this relates to AI. I mean, all the AI that we know, it has been built by humans. So in some sense, they're not all that different from us. We built them as little compact objects that sit in a laboratory, in a computer, if you wish. And I don't think there's much to find, at least at the moment. But I mean, if there are some kind of alien beings who are not bound to bodies in one way or another, like we are, I think it's conceivable that they would have a different notion of entropy.
I don't know if you saw the movie Arrival. It's based on a Ted Chiang story called Story of Your Life, but in that there are these aliens and they perceive time differently. They basically perceive all of time at once. And there's this woman, the scientist or linguist or something, and she learns their language, and then she, in the process of learning their language, she learns to perceive time the way that they do. And I was just curious, what do you think about that idea of aliens who would perceive, who would not be moored in a specific present, but would kind of like experience all of time at once?
So I'm afraid I don't know the movie, but it's a very interesting idea. Of course, this is very strongly linked with the notion of entropy, because at least the way that the argument currently goes, the reason that we have this perception of the present moment being special is that entropy increases, at least for us. I guess if there were any such aliens, they would necessarily have to have a different notion of entropy, because in some sense, we use entropy to define the era of time. Why is the past different from the future, and why does there seem to be a boundary between the two? Why do we only have a memory of the past and not of the future? And so to overcome this, you kind of have to change something about this notion of entropy.
Yeah. So Arrival, that was one I was curious if you'd seen. And the other one, I don't know, this is a little more obscure, so maybe you haven't seen it, but there was this TV show called Devs. It was Alex Garland's. He's one of my favorite directors. But the premise is that there's this Silicon Valley company, and they've developed this algorithm basically which predicts the future perfectly. And since causality is deterministic and everything, like everyone who's seen this simulation running knows all these horrible things are going to happen, but they're completely helpless to do anything because it's always right to change it. So I don't know if you've seen that or if you have any thoughts about that. idea.
You know, I'm totally hopeless with movies and TV shows and everything. I don't watch anything. The only occasion that I ever got to watch movies was on a plane, you know, a long distance flight overseas, which I haven't been on for you know, since pre-COVID times. So you could throw all kinds of movies at me, and I would always say, "Sorry, I haven't seen this. Sorry, I haven't seen this." That's a very interesting idea, which in my book I also briefly touch on this. If this would actually be possible, can you actually predict the future? It's kind of depressing, right? So but this brings to my mind, I recently read a graphic novel, like with cartoons and stuff, which was based on the same idea, and it'll be published next year, I think. It's called The Phantom Scientist. I understand it's a translation from French, and it has the same idea. There's some guy who's developing computer code that can predict the future, including his own future and that of his collaborators. And in the end, everything goes badly wrong. But so this is the idea. It's certainly intriguing. Is it possible? I mean, there's always this argument that has been put forward many times, that if you have a prediction for a system in which some parts know of the prediction, then they can act so that the prediction doesn't come true. And I think that's actually correct. The problem is that it's basically it's an open system, right? So you're inputting the information from your computer code, which made the prediction, into the human, which then alters the initial condition that the prediction was based on. And so for the complete system, you can't really make a prediction if you do it this way.
Well, but I think the thing is, if the simulation is modeling everything, then it's modeling and taking into account the fact that the humans are going to find out about the predictions, and that's going to alter the course of the future and so on. I mean, like, because
but hang on. This creates a feedback loop which might not converge. You know what I mean? There just might not be a prediction coming out of this requirement. The simplest example is this idea that I make you a simple offer. You either eat the marshmallow or you don't. And I make a prediction, which is you take it or you don't take it. And you know my prediction. You can do the opposite. So you can iterate this as often as you want, but the prediction will never fit to what you actually do.
Well, because in the book you talk a lot about free will, and your constant refrain that you have is you say, the future is fixed, aside from random quantum events that we can't influence. And so, I mean, if the future is basically fixed, then presumably it could be... Yeah, I don't know. It's weird to think about, but
So what you could do is you could take your prediction device and the human and the marshmallow and whatever, and put this together in a box, which is a closed system, and then you can make a prediction for that. Mm-hmm. So this will work. But what I'm saying, what doesn't necessarily work. I mean, there are cases where it does work because you just do what the prediction says you do. Okay, so then there's no inconsistency. But if you give the prediction for what a person will do to the person, then the person can do something else based on this input. And so it creates an inconsistency. There's nothing scientifically wrong with it. What happens is just that the initial condition that you used to base the prediction on is not the correct one, because you hadn't taken into account the prediction, that the prediction is handed on to the human.
Yeah. Do you think that Do you think, I'm just from reading your book, do you think that the concept of free will is just basically an incoherent concept? I mean, can you imagine any hypothetical intelligence or universe where you would say that there actually is free will, or is just like causality just a basic fact of any possible reality, and as long as you have causality, you're never going to have free will?
I can imagine it, yes, but for all I know, it's not realized in the laws of nature that we have found so far. So one possibility, so the basic reason that I find it hard to make sense of free will, given what we know about the laws of nature, is that the laws for the microscopic constituents, for all we know, give rise to the behavior of macroscopic beings. Or to phrase this in a simpler way, you're made of particles, and we know what the particles do. Therefore, at least theoretically, in principle, we know what you're going to do up to those random quantum events. And that's basically it. And that seems to be how the laws of nature work in our universe. But it doesn't have to be that way. The laws of nature, it could be different than that. And one way that they could be different is that this derivation of the macroscopic behavior just fails at some point. So basically, if you, to give you a simple example, if you get to objects that are beyond a certain size, because you just can no longer calculate what they do. And what would happen is that you would have to introduce an entirely new set of laws on this macroscopic level. And that might allow you to actually reasonably define something that you could call free will. But as I said, for all we know, the laws of nature in our universe don't seem to have that property.
Mm-hmm. But so even in this hypothetical universe where you couldn't predict what the macroscopic object was going, or character or whatever was going to do from the behavior of the particles, wouldn't all the inputs still be causal? I mean, like where would the character have the ability to not do something that was defined by something that had happened earlier in time? You know what I mean? I don't know if that makes sense.
You're asking, like, what would the law look like for the macroscopic whatever? I don't know. We don't live in this universe. So, I mean, one possibility that I've, pulled out of a hat at some point, like 10 years ago or something, is that you can have a kind of an information reservoir that doesn't reside inside of time. So basically, every time you come to a branching point, you pull on this reservoir outside of time to make your decision, and that would not be determined by the past because it's not in time. Does that make sense?
Yeah, well,
but it's just, it's really completely made up.
Yeah, but I mean, I don't know. Wouldn't the thing? I don't know what does that mean for something to be outside of? I mean, it would still something would have caused it. This is maybe getting too abstract and philosophical, but it did make
right. This would get us into a long discussion about what we mean by cause to begin with, because there are at least two different ways that people talk about cause. And at the moment, I'm not sure which way you use the word. So when I talk about free will, I don't talk about causes at all. I talk about determinism, like what is determined by the past.
Okay. Well, maybe we should move on to another subject. But I mean, that's interesting that, at least in theory, you think that we could have, there could be some parallel universe with different laws that would have, but you don't think in our universe, even no matter what the biology was, no matter what the AI was or anything like that, you don't think there could be any real free will in our universe?
Well, it's always possible that we find out something new about the laws of nature that changes the story. So what I'm saying is that according to all we presently know about the laws of nature, free will just doesn't make any sense. But I mean, I can't reasonably rule out that this is going to change at some point in the future.
Hmm. One of the ideas in the book I thought was really interesting is this idea that we could maybe create our own universe in a lab, that we would sort of kick it off and it would instantly blink out of existence, but it would be expanding off in some other dimension or something. And I guess creating billions of stars and worlds and all that. Am I understanding that correctly?
Yeah, it wouldn't blink out of existence. It would just lose connection to our universe, so we would no longer be able to communicate with it. And yeah, so it's one of the consequences of the theories that we believe describe how our universe was created. So if those theories are correct, which is a pretty big if. Okay, I want to point this out. Then there is nothing in principle that would prevent us from also creating a universe. I think when I talked about this the first time, people thought I was kidding. Because I'm kind of known to always say, no, this is bullshit, you can't do it. But in this case, it's actually correct. And I think the reason that people get confused about it is that naively it seems you need a huge amount of mass or energy to create a universe, because where does all this stuff come from? And this just isn't necessary in Einstein's theory of general relativity. The reason is that if you have an expanding space-time, it basically creates its own energy. So energy is not conserved. It's as simple as that. And you can estimate, and people have done that, and I have all the references in the book, how much mass you'd need to create a new universe, and it turns out to be something like 10 kilograms. So that's not all that much, except that you have to bring those 10 kilograms into a state that is very similar to the conditions in the early universe, which means you have to heat it up to dramatically high temperatures, which we just currently can't do.
Mm. I don't know if you're familiar. There's a movement now called effective altruism, where the idea is, rather than just spending money on charity and philanthropy willy-nilly, we should be doing a sort of utilitarian calculation of what charities or whatever benefit the most, do the most good for the most people. And so I sort of, spending money on mosquito nets to prevent malaria might be the best use of your money rather than something else. So that was kind of making me think, well, maybe creating new universes would actually be the most philanthropic, charitable thing you could do, right? Because for however much it costs to create a new universe, you're creating trillions of planets and lives and everything. So maybe we should be directing a lot of time and energy toward that.
Yeah, well, the problem I have with those arguments, and I've read about them, is that you have to think about the opportunity cost. Like if we were to do something like this, I mean, leaving aside that our technology just can't do it. Suppose we'd spend a lot of time trying to make our own universe, but eventually fail. All that money was not spent on making living beings in this present world better off. So
you're not in favor of
well,
too much
to some extent, but I think you have to take into account how speculative the idea is that you're running after. And in the case of something that's as speculative as making a new universe, I would say that the risk is just way too high that you're going to waste all that money. It'd be better to spend it on something that we, are a little bit more certain will actually benefit people.
Okay. All right. Fair enough. So do you think, one of the things I thought was in terms of like universes being created and everything, there's a lot of discussion in the book of is our universe fine-tuned, and is it fine-tuned for like number of black holes, or for the existence of life, or or for the existence of computation, which I thought was interesting, which kind of, as a science fiction fan, kind of made me wonder, well, is it possible that AIs created our universe to be particularly fertile ground for AIs to arise, and the fact that we exist is just sort of a byproduct but the actual goal was to create computation. So I was just curious what you think about that idea.
Well, those are all interesting ideas, and I love speculating about them. But I think one has to be careful to not confuse them with science, because there's, if you throw out an idea like maybe our universe was created by some AI to maximize computation, how would you ever test this? I can't think of any way to test it. It sounds to me like a very technocentric type of religion, and there's nothing wrong with it, but it's not really scientific. So I would say, if you have fun talking about this kind of stuff, it's fine with me, but don't pretend it's got something to do with physics.
Because that's something you talk about a lot in the book, is I guess you feel like a lot of scientists have been kind of overly enthusiastic about talking about ideas like the multiverse or the simulation hypothesis, without, I guess, giving a emphatic enough disclaimer that this is just sort of wild speculation. Is that a fair summary of your argument?
Yes, though I have to clarify that I think in many cases they're not fully aware of what they're doing. I think there's a certain lack of philosophical underpinning that's driving this, especially when it comes to the multiverse. I do know quite a lot of cosmologists and astrophysicists who actually believe that other universes are real. And I think it's a misunderstanding of how much mathematics can possibly do for us. So they seem to have this idea that just because we can write down the mathematics for it, and some of that mathematics agrees with what we observe, therefore everything else in that mathematics must also be real. That's just not a conclusion that the mathematics actually allows. It's not a scientific argument. So I don't want. There are certainly some people who have been pushing this line a little bit too far, probably deliberately because it sells and so on. But I think for most of them, I think they're genuinely confused.
Mm-hmm. But so you think would it sort of satisfy your criticism if they were just to add a more emphatic disclaimer, like this is just a theory, we have no experimental evidence to back it up, it's fun to talk about, but it's not really science in the strictest sense? Like is just a disclaimer like that you want, or do they need to, like, is there anything else you think that they should be doing to
that's basically it. If they were just to say, look, people, we believe in this, but it isn't really science, that'd be fine. Because what happens, I think, is that people who are not physicists, they understand just fine that this isn't science, because not only is there no evidence for the existence of other universes, there will never be any evidence. It's an untestable hypothesis. And most people know enough about the philosophy of science to understand what the problem is with this. And now, if you have scientists going around and talking about this as if it was science, I think it just erodes trust in science in general. And I think that's a very bad thing. So if they were just more honest about, look, this is a metaphysical assumption. It's not strictly scientific. There's no empirical evidence, and there will never be empirical evidence. But we believe it anyway because, I don't know, we trust our mathematics or whatever their reason is. That'd be fine with me.
I just, a year or two ago, I interviewed Katie Mack. And I just went back and listened to my interview with her, and she was saying, this is I think, a real long shot, but she was saying that she thought that there was some possibility, like a non-zero possibility, that we might get signals from other universes with gravity. I don't know what you think about that, but is that just generally agreed among scientists? You think that there's like no possible evidence for other universes that could ever possibly be detected? Or is there some disagreement about that?
Well, there are some cosmologists who have made up particular models for the multiverse in which other universes could collide with our own, or our universe could be entangled with another universe. And in those cases, you can come up with observable predictions. And, well, people have looked for the signatures of those other universes and they haven't found any. So to the extent that those ideas were falsifiable, they have been falsified. Now, you can always make up other models for that kind of thing, which is kind of a somewhat different philosophical problem that physicists run into there, where they just, invent mathematics and proclaim it's somehow testable. And so I think all those alleged predictions are rubbish, but it's for a different reason than what I was previously talking about, which are those unobservable multiverses. It's basically that you're just guessing something. There's no reason why this guesswork should be correct. It's just not a scientific method of producing a new model. So that to me is absolutely unsurprising that those ideas are just falsified one after the other.
Mm-hmm. I mean, is it not part of, like, do you consider it part of this, like, sort of out there thought experiments to be part of the scientific method ever? I mean, like, I obviously I'm not a physicist, but, like Einstein would think, like, oh, if I was on a train traveling at the speed of light and I, like, looked, what would I see? Like, stuff like that, like, that sometimes, like, thinking about really outlandish things leads you to real scientific insight.
Yeah, certainly. Thought experiments are all fine. This isn't the problem. The problem is the thing that they are trying to test. So there was absolutely no reason why this should actually describe reality. And there are literally infinitely many mathematical ideas you can write down and that you can proclaim might describe reality, and you could go and test them. But what do we learn from this? Nothing, really.
What do you make of, I mean, you mentioned in the book, like, with the simulation hypothesis, which is that the idea that we might be living in a computer simulation, you talk about people like Elon Musk and Neil deGrasse Tyson saying that they think there's a better than 50% chance that that's true. Like, what do you make of that?
Well, it's one of those ideas where I'd say, if you want to discuss them on the level of philosophy, or maybe over a glass of wine at dinner, because it's fun to talk about, is all fine with me. I get a problem if they argue that it's based on a scientific argument, which is not the case. And those arguments for the simulation hypothesis, in all forms that I've seen them, they always rely on some statements about how the fundamental laws of nature work, and that's territory of physics. So I feel like I have something to say about it. They implicitly assume that it's kind of simple to reproduce all the observations that we have made in the entire universe, everything from general relativity and quantum mechanics and so on and so forth, by an algorithm that you can put on a computer. And I would really like to see this algorithm, because it would be a theory of everything. And last time I looked, we didn't have one. So how do they think they're going to do it? And there's also a lot of hand waving and fudging going on when they're talking about the computational capacity So it's one of the obvious problems that you run into is that if you create a universe with conscious beings inside, and those conscious beings create universes with conscious beings and so on and so forth, then you run out of computational capacity really, really quickly. So those arguments that we live in a computer simulation, they usually have some kind of assumption that if there's some part of the universe where no one's looking, then you don't really have to do the entire calculation. You only have to fill it in if someone's trying to measure something. And now this brings up the question, like, how do you know when someone is looking at a particular piece of the universe? How are you going to do this reduction? And there are lots of other problems. For example, if you look at weather or climate models, those are chaotic systems. And to make matters worse, if you look at the Navier-Stokes equation that is being used for the atmosphere, but also for ocean currents and so on and so forth, this equation is very, very difficult to put on a computer because it has this weird property that it doesn't care about scales. So we say it's scale invariant, and this is why you have these large and small turbulences. So what happens if you put it on any kind of grid on a computer is that you're cutting off part of this complexity. And this has the result that the computer simulation does not agree with reality very well. And this is like a huge unsolved problem that people cope with in reality every time they make a weather forecast. And it's one of those problems that people who talk about the simulation hypothesis just completely ignore. They're like they've never heard of chaos.
Right. I mean, it seems to me just like from a science fiction perspective, if you had a simulation and you were in charge of it, you would have basically complete control over everyone in it. It would be like, like you mentioned the movie Dark City, where people wake up every morning and there's somebody completely different because they've, the parameters of the simulation have been changed overnight and they're not aware of it. And so it seems like you could have just sort of a rough approximation of reality. And anytime somebody noticed, you could just like wipe their memory and roll back the clock 24 hours and have it go so that they wouldn't notice it, like with World of Warcraft or something. If there's a big bug, sometimes they'll just like roll the whole thing back 24 hours to how things were then, because it's easier to do that than to try to correct it after it's already gone wrong. So it just seems like, if you were inside a simulation where you might be at the mercy of super intelligent AIs or like whatever, you would be so manipulable that, it would be hard to ever know whether you were in a simulation or not.
Yeah, but again, I would like to ask you, like, how does it work in practice? So you've just invented a programmer who, looks at, I don't know, several billion conscious beings and figures out if one of them has noticed something that doesn't quite fit together and then rolls back the simulation by 24 hours or something like this. It doesn't seem particularly feasible. At the very least, I would like to know how is it being implemented? So you see what I'm saying is that on a vague storytelling level, like the way that you just did it, it's all fine with me, and I, I like speculating about this kind of thing as well. But I don't think that it's actually based on science. So if people go and spit out numbers, like I think there's a 50% chance we're living in a simulation, I'm not having it, as a physicist who has to think about how you actually simulate the reality that we observe on a computer. I'm telling you, it's not easy, and it's not a problem that you can just sweep under the rug.
So do you think the chances we're living in a simulation are zero, or do you think it's not calculable, or is it non-zero but very low, or?
I don't know. I would say the error bars are so large on that kind of thing. There's no scientific statement that you can make about it. Mm-hmm. So I guess the answer is we don't know.
Mm-hmm. I guess one thing I thought was kind of cool was this, there's these sort of things in science fiction that you have sometimes that, people predicted in the 50s or whatever, like jetpacks and flying cars and stuff that never seem to come true. But, and I'm at the point now where I don't really expect them to ever come true in my lifetime. But you actually mentioned weather control is one of these things. And you say, like that we actually have a pretty good idea of how we could, say, interrupt a hurricane before it gets really big and destructive. And we just can't currently, our prediction models currently aren't good enough to actually do that. But it seems like maybe it's not too far beyond the realm of possibility that we might be able to do that if the prediction models keep getting better and better. Is that, I don't know, is that right? Do you agree with that?
Yeah, but before I talk about weather control, have you watched the videos from this British company with the jetpacks?
I'm not sure which one you're talking. I've watched a lot of jetpack videos.
Yeah, well, I've forgotten the name, but I was really impressed by those. It's the guys who are flying over the what's it called? It's a national park in the UK. Something with the Lake District.
I'm not sure. I mean, because the problem with them is that like they look really cool, but then you can only fly for like 10 or 15 minutes or something. So it's
right.
But they're pretty
something
cool.
like this. But I was impressed how well it worked. Also nice scenery, but yeah, completely off topic. So the thing with the weather control, this was an off spin of a video that I made about cloud seeding and can we stop hurricanes? And I found out that it's actually pretty well understood how hurricanes form, and a lot of efforts have been made to stop them. And the big showstopper is that at the moment, when we know what kind of cloud wind configuration is with very high probability going to turn into a hurricane, it's too large to do something about it. And we're talking about large, like these things are really huge. And there's stuff you can do, and this is something that people have looked at, for example, like putting a particular type of biodegradable oil on the water. Why does it stop a hurricane? Because the way that the hurricane grows large is that the water is warm and evaporates, and it gets pulled upwards, which drives the circulation of the thing. So it's a positive feedback loop that makes the thing bigger and bigger, and there's more and more moist air going around in a circle. So if you put some kind of oil on the surface of the water, it stops the evaporation. The whole thing just, the whole cycle stops working, and the hurricane dissolves into wet air, basically. But the problem is that you would have to cover a huge surface area of the water, which is completely impractical. But if you could actually predict what's going to turn into a hurricane when they're much smaller, it might be feasible. And I've talked to meteorologists and climate scientists who have looked into this kind of thing, and it seems to be the case for other situations too. Like in principle, it's known how you could influence certain types of weather phenomena, but the problem is that the predictions aren't good enough at the moment. And you know what? I'm actually pretty sure that we will see more and more weather control in the near future. For example, this issue with the cloud seeding. So you make water rain off earlier from the clouds than it would normally be the case. It's going to become a really big issue when droughts become more common, because every country will try to make clouds rain off over their territory, and it's going to cause a lot of international problems.
I didn't watch that video, so I'm not sure if you talked about this or not, but one of the interviews I did years ago, it was a book about Kurt Vonnegut and his brother. Mm-hmm. And his brother was a scientist who was actually doing experiments with cloud seeding to make it rain for farmers. And it actually worked pretty well. Like, it didn't work well enough to really be worth doing it, but it you know, he was having some success with it. So, and it's interesting because how that influenced like Kurt Vonnegut's book, Cat's Cradle and stuff like that was really interesting.
Yeah, it's right. It actually works. And the Chinese are investing pretty heavily in cloud seeding, and at least the last time I looked at it, they had a pretty big program running on it. And if they're starting to do it, then other countries pretty much will have to do it too. And at this point, we're already deep into trouble, I guess.
Yeah. I also really want to ask you, so within the last year or two, we reviewed Ursula Le Guin's novel, The Dispossessed. And a big plot point in that is the invention of this device called the Ansible, which allows instantaneous, you know, like faster than light communication. And I was just wondering what you thought about that idea, because you're talking about in the book, you talk about like the idea that the whole universe is a giant mind and that you could theoretically have communication faster than light. But then you also say a lot of people will talk about quantum entanglement as a means for faster than light communication, and you say that that's not happening. So I'm just curious, do you think that humans, like, what would you say the chances are that humans will ever be able to send messages faster than light?
I think the chances are pretty good, but it's probably not going to be with entanglement because, I mean, you can mathematically prove that you can't send information faster than the speed of light with quantum entanglement. So quantum entanglement it's a non-local correlation, but it's locally created. So you can't actually send information with it. But I think that physicists are a little bit too fast throwing out faster than light communication, because there's a lot that we don't understand about locality. So we briefly talked about wormholes earlier. And so I'm not a big fan of big wormholes, you know, where you could go in on one end and come out on the other end. But if space-time has some kind of quantum structure, and pretty much all physicists I know believe that it has, so for which we would need this theory of quantum gravity, which we still don't have, and so on, it's quite conceivably the case that it would not respect the notion of locality that we enjoy in the macroscopic world. So on this microscopic quantum level, when you're taking into account the quantum properties of space and time, distance may just completely lose meaning. And I find it quite conceivably possible that this will allow to send information faster than light.
Because in the book you say, you're talking about these kind of like mini wormhole things, and you say these non-local connections would be too small for us or even elementary particles to go through. So like what would you send through to send a
That's
signal?
right. So we basically know this already, because otherwise we'd have seen it. So if every once in a while there's something vanishing into nothing, we'd probably have noticed. But I mean, you have to keep in mind that the elementary particles that we have seen so far, so those are the smallest things that we have ever measured. It's stuff like the quarks and so on that we see at the Large Hadron Collider. They're still huge compared to the size that we believe those quantum fluctuations of space and time would have, which would be at the Planck scale. So there's still like 20 orders of magnitude in between. And yeah, so what would you send through? Well, the geometry of space-time itself carries information. And so we don't normally think about this, but gravitational waves are basically an example for this. So this is it's a deformation of space-time itself that when it arrives on Earth, we convert it into a message that we can read out in terms of material, basically massive objects, the normal particles that we deal with in terms of detectors.
Because you mentioned this in the book, but what I had always heard is that you wouldn't be able to send information faster than the speed of light because it would violate causality, because then you could get into situations where the information was received before being sent and stuff like that. And I think you said in the book that this wouldn't violate causality, but I'm not sure. I followed the argument, but I don't know if it's something you could summarize quickly. But
what I write in the book is that it's compatible with Einstein's theories, and the reason I write this is that I don't know why, but a lot of people seem to think that Einstein's theory forbids faster than light travel or exchange of information. It's not the case. What Einstein's theory tells you is if you have something that's slower than the speed of light, you can't accelerate it to a speed that's faster than light, basically because it would take an infinite amount of energy. But it doesn't a priori forbid anything to travel faster than the speed of light. You still have potentially problems with causality. There are scenarios that you can make up where it would happen, but those are fairly easy to get rid of just by saying, well, it can't happen. So the only faster than light signaling that you can do is that which does not lead to causality paradoxa. And the interesting thing is that those situations exist, and it's actually not it's not difficult to get it done, simply because in Einstein's theory of general relativity, so not the special one, we do have, for better or worse, a preferred frame. That's what it called. It would be the rest frame of the cosmic microwave background. That's what people usually use. Could be a slightly different frame, but it doesn't really matter. So what this frame does for you, it tells you what's forward in time and what's backward in time. By the way, this brings us back to this issue of entropy, which is also believed to define an arrow of time, and how those two belong together is a kind of an unsolved problem. But as a matter of fact, we do have an arrow of time in our universe. Like, we experience it, we observe it. And you can use this arrow of time to say, well, you can only send information faster than light if it goes forward in time and not backward in time.
Yeah, well, that's cool. This has been a really encouraging conversation. I mean, that, faster than light communication might be possible. The universe might not end.
This makes me so happy. You won't believe this, because this is exactly what I was hoping to achieve with the book. I was trying to say, physics isn't just something that tells you stuff that you can't do. It sometimes opens your mind to new things that we might possibly one day be able to do.
Yeah. Yeah. Well, no, this has been a big up, brought up my mood a lot. All right, we're almost out of time. I guess just the final thing maybe I'll ask you about is, you say that you think that science could learn from religion, that people need communities, and that scientific events and and communities and things should be more social and making more connections between people and stuff. And I agree with that, because I go to a lot of lectures and things, and then you just kind of sit in the audience, and then you leave, and you never meet anyone else there, except maybe under unusual circumstances or something. But I'm just curious if you could talk about, how do you think that science could be more community focused?
Yeah, that's right. I think that science is really not very well integrated in people's everyday life in a way that the church religion does very well. Like they care about people, like they bring them together, they organize events, and of course people like it. And when I was at Perimeter Institute in Canada, they had a weekly public lecture, which it was on the weekend. So at a time when people could actually come, and not during work hours. And afterwards, there was a brunch that everyone would have together. And I know that the people who would attend those lectures, they would go there regularly, and they would appreciate the opportunity to just sit together and talk with other people who were interested in the same things. And this is something I think that scientists take for granted. Like we have all our friends and colleagues that we talk to about the stuff that we're interested in. But it's not the case for everybody else. Some people who are interested in, I don't know, quantum mechanics, maybe they don't know anyone else who's interested in quantum mechanics. And to some extent, there are online communities which fulfill this task now, but of course it's still better to actually meet with people in person, and I think that science could be so much better at doing this than it currently is.
Yeah, absolutely. I totally agree with that. And yeah, if anyone listening to this is involved in organizing events of this kind, yeah, definitely it would be great if there were more opportunities for attendees to socialize with each other. I think that'd be really great. All right, so yes, why don't we start wrapping this up? Do you have any other final thoughts or any other projects you want to let people know about?
No, not really. Oh, maybe since we were talking about the multiverse at the very beginning, I have a video coming up about this in 2 weeks. So not tomorrow, but on September 10th, where I go through those arguments and explain it in a little bit more detail than I did now.
Okay, cool. Yeah, so everyone... Oh, I guess I could mention your YouTube channel. It's called Science Without the Gobbledygook. So everyone can keep an eye out for that video. And so we've been speaking with Sabine Hossenfelder about her new book, Existential Physics. So Sabine, thank you so much for joining us.
Thank you so much. Wonderful to talk to you.
And that was our interview. So big thanks again to Sabine Hossenfelder for joining us on the show. This episode of Geek's Guide to the Galaxy was made possible thanks to support from listeners like you. So if you enjoy the show and want it to continue, please support us on Patreon over at patreon.com/geeks or via PayPal over at geeksguideshow.com/crowdfunding. Alright, so that was our show. So thanks everyone for listening, and we'll see you next time.
The Geek's Guide to the Galaxy is a production of Wired.com. For more information about the show, visit geeksguideshow.com. To learn more about your host, visit davidbarrkirtley.com. Music and voiceover produced by yours truly, Jack Kincaid. If you enjoyed this program, tell your friends. If you didn't enjoy it, tell no one. Thank you for listening.